Hello friends, let's start with the introduction of material science and engineering, the course we want to cover in this particular lectures. Okay, so if you want to see the objectives, that what you will be able to do after the completion of this course, okay, so that will be that you will be able to distinguish between crystal structures. Okay, we will see some of the terms you may not be familiar with. We will see during your course that you will be able to understand all these terms. Okay, what do they mean? Okay, and in fact you should be able to use them for your purpose. Okay, so first will be that you will be able to distinguish between crystal structures. Here we will be taking only the metallic materials. Okay, there are other materials also, for example ceramics and so on. So in this we will be only concentrating on mostly on crystal structure found in metallic materials. Okay, and that is some very simple crystal structures are there. Then one of the most important thing is that you will be able to correlate structures. Okay, so basically the crystal structure, the microstructure, okay, and the mechanical properties of a material. Okay, so again as you can see that mostly in this course we will be concentrating on the mechanical properties rather than other properties, for example magnetic properties or electrical properties or optical properties. Then we will be able to predict material response to external environment. Okay, it can be mechanical environment, okay, where you have load or stress on the material. It can be thermal environment, okay, that means the material is exposed to high temperature or very cold temperatures. Okay, so what is its response? Okay, and you should be able to also predict that response, okay, that the material will do something like this, okay, in this particular condition. You will be able to identify properties required for a specific application. Okay, so when I give you an application, okay, we need a material for, let us say, automobile application. Okay, maybe the structure of the automobile, or let us say I want a material for axle, the axle of the automobile, okay, which continuously is rotating. Okay, so when it does this kind of rotation, it is subjected to a condition what we call as fatigue loading. Okay, or a material may be exposed to high temperatures. Okay, again taking example from the same automobile. Okay, a material which is used in, let us say, cylinder head or a piston which goes into the cylinder, actually which supplies the power to the automobile. So all these materials have to undergo or see the condition of high temperatures. So we should know that which properties will be required for particular application. Okay, so by knowing that what type of loading is there, what type of conditions are there, I would be able to give that, okay, my material should have these properties. Okay, at high temperature you should have good thermal conductivity, it should have good creep properties. Okay, all these terms you will be able to understand during the course. Okay, then you will be able to propose mechanical and thermal conditions or processing conditions basically to tailor microstructure in order to modify mechanical properties. Okay, so one of the very beautiful thing about materials is that the properties are not constant. So if you take one material, you cannot say that, okay, this material will have only this type of property. Okay, I can change the properties. Okay, and that is what is the when we talk about materials or basically engineering materials. Okay, I can change properties. For example, some natural occurring material, for example wood cannot be, you cannot do any too much variation in the properties. You can do some, okay, not much, whereas all the engineering materials which we have, okay, which we use especially as structural materials, okay, you will see that by doing different type of thermal mechanical treatments, I can change the microstructure. Again, the microstructure term you will be familiar with once you complete this course. Okay, so I can tailor those microstructure, and actually I can also get the desired properties by doing this change in the microstructure. Okay, and some thermal mechanical treatments can do that. Okay, so we have to understand first that what is the response of material to these condition, so that once we know the response, we will be able to modify the response of the material by altering the microstructure. So that is one of the very nice thing about engineering materials, that you can do all these things. Okay, and you have to have a good understanding of materials for that. Okay. Now historically, if you see, materials actually define the civilization of human. Okay, so human civilization is actually divided according to the material they were using in that period. Okay, for example, the early humans started using stones to hunt animals, sometime to break whatever they have into small pieces. Okay, so they could see that some rocks are you can get very fine edge in some rocks. Okay, by chipping it with another rock, I can get very sharp edges in some rocks. Okay, not in all rocks, few rocks are there like that. So they could identify that. Okay, and then they created these very sharp edges in that. Okay, and that can be used for hunting. Okay, that can be used for breaking the bones, for example, of animal which they have hunted. Okay, so they started using stones. So the early age human civilization is defined by a stone age. Then people started seeing that some material are other than stones are also existing in their natural form. Okay, so gold, silver can be easily found out from the mines. Okay, and they are not forming any compound, they are as gold nuggets or silver nuggets and so on. These are inert materials, so you can just get it from the mines in their natural condition. Okay. Then later on, people started actually after mining they could get ores. Okay, and those ores can be treated to extract the material out of them. Okay, and then that is how they started extracting copper and so on. Okay, and from there the bronze age started. So it is basically an alloy of copper, okay, with tin or aluminum and so on. The aluminum came much later. Okay, so then the bronze age started, and you can see that whoever perfected this technology, they started dominating the others when they had this kind of technologies. So material actually gave edge to a particular civilization which started dominating the other civilizations. Okay. Then of course iron age came. Okay, iron ore was in some oxide form. Okay, so to take out iron from iron ore, okay, you had to have technology for that. Of course, India, some tribal part of India had this technology for a very long time. Okay, and they were able to make this iron. And actually, if you have gone to Delhi, okay, close to Qutub Minar, there is a iron pillar, okay, which is existing there for 400 or 500 years. Okay, and it is still not rusted. Okay, so it has a very good corrosion properties. Then after iron age, actually lot of materials then started coming out. Aluminum was able to can be extracted from its ore. Then the plastic age started. So very completely different type of material from the materials which were in existing from up to that point. So then lot of plastics were started being used in engineering applications or in daily products also. Okay, and then of course electronics started dominating. Then we start calling it as silicon age. Okay, so now people will debate that people can refer to these changes in different forms. Some may say now it is not materials. Okay, and you can call it as electronic age. Why you are calling it as material age? The idea is that some kind of material started dominating that part of the civilization. Okay, so that is how you can get different ages. And one good source is also already listed in the bottom here. which can give you much more detail about this history of materials. Now, if you want to see the importance of materials, okay, I have taken here couple of examples, okay, and I am trying to cover a very broad range to kind of get you a hang of materials, and also to make you appreciate that materials are not only structural materials, and it is not only about some engineering application kind of. A lot of time it is aesthetics also, which can like dominate that how the material has to be synthesized. Okay. So, let us take an example of defense application right now. Okay. So, you must have heard about intercontinental ballistic missile, ICBM, which has a very high range. Okay. And right now, if you are going through newspaper, there is a lot of tension between North Korea and USA, okay, that they are able to make a missile which can go up to USA. Okay. So, it has to cover a very long distance, okay, and for that it has to go into a very rarefied atmosphere and then come back into the atmosphere. Okay. And also you want your missiles should not be intercepted by other missiles or maybe a fighter jet. So, you have to take it to very high altitude, and then it has to re-enter the atmosphere. Okay. The problem is that when you re-enter the atmosphere, because of the friction and your very high velocity of the projectile, the heat generated at the surface is very high. Okay. So, it can be in excess of 1500 degrees Celsius. Okay. And most of the materials which we use or know, they kind of melt at this temperature. Okay. So, you have to have a material which can be used in this kind of missile nose. Actually, nose gets heated up to this high temperature because that is what is seeing the friction of the air. And now you can understand that I have a technology to launch a missile. I have a whole jet propulsion technology. Okay. But I do not have the material which can withstand that temperature. So, my whole technology is waiting for the material development, and all these are not easily available. A lot of these are classified information, and countries do not give it to each other. So, you have to develop your own materials, okay, from the know-how you have about the materials. So, that is how reinforced carbon-carbon composites were developed to coat or to cover the nose part of the material, and these are able to withstand this kind of very high temperatures. Okay. Another example now from space. So, again you must have heard about GSLV Mark III, okay, recently launched with a very high payload and large number of satellites. Okay. And again, for developing this kind of rocket, there were other rockets are already developed which were working on the solid propellants. Okay. Now, to have a higher payload capacity and higher range, okay, you want a engine which can directly take liquid hydrogen and oxygen, combine them together to generate the thrust required. Okay. And now, hydrogen and oxygen is of course in gaseous form at room temperature, but at very low temperatures, cryogenic temperatures, they are in liquid form. Okay. So, now my material development has to be such that it is able to handle that temperature, because you have to store hydrogen and oxygen within the rocket, okay, and they are going to combine and give you the thrust which is required. So, and of course, when you must have seen when the rocket gets launched, there are so many vibrations, and it has a very high thrust. Okay. So, the material has to withstand those kind of vibration, those kind of mechanical stresses at a very low temperature. Again, it will be dependent on the material development. So, the technology is very simple. You have hydrogen, oxygen, you are combining to get the required thrust. Okay. But the material which will be required for storing these material at such a low temperature, okay, so you have to develop those materials, and there are few titanium alloys are there which have very good property at cryogenic temperatures. Okay. So, again a very different example then. So, you have coming from very high temperature application to a cryogenic application. Okay. Now, let us take a very popular product. Okay. So, Apple Watch was a craze, I think a couple of years back, okay, when they launched it, and if you might have seen the videos, the initial promo videos which were there on the internet from Apple, okay, they kind of, for a very significant segment of that video was devoted to metallurgical developments which they tried for making this watch. Okay, they were talking about high strength aluminum alloys, they were talking about metal matrix composite of gold and ceramic, okay, because they wanted to have a lot of gold coating on the surface and they wanted it to have a very good hardness. Okay, gold is very soft and it has a very low strength. Okay, that is why you do some alloying to increase the strength. So, what they did is they added ceramic particles in that to increase the strength and to have a good scratch resistance, okay, and also to give a nice hue to the surface of the this watch. So, they developed all these aluminum alloys, high strength aluminum alloys. Of course, some were already developed, they might have used it or they might have developed also, because they did not give any details of these alloys. They use stainless steels. Okay. So, the idea is that from a very defense space to a very popular product, okay, and they are talking about materials. In fact, this Apple is talking about material development. Okay, and as far as I am concerned, if somebody is using a certain thing in his in the advertisements, that means it has come to a certain level, okay, and that you are able to use that in the advertisement and you want to advertise the material as such. Okay. One of the biggest kind of change which Apple brought is in terms of, for laptop also they used aluminum cover. Okay. So, till that time it was only plastic cover were there for the laptops. So, they brought in aluminum and these were anodized aluminum, again very good scratch resistance is there. So, it will not with the time it will not, the surface will not be looking bad, okay, and it will be looking as a new laptop. Okay. So, from plastic again you can see that now metals are again coming into the vogue, okay, and people are using and advertising them. Okay. Another very different kind of flavor, if you want to bring it to this discussion, that material behavior in biotechnology. Okay. Some you must have already seen that people use prosthetics, if something, if you have some problem in bone, you have some kind of implant there. Okay. But sometime now people are also using the material concept to know that whether you have some kind of disease or not. Okay. So, for example, one example is here, the source is listed in the bottom, okay, where they are trying to see that this is RBC cell, okay, red blood cell, okay, in the middle, and there are these two tweezers. So, these are actually laser tweezers, some very sophisticated experiments they have tried. So, this is a RBC, okay, and there are two tweezers and they are deforming this cell. So, you can understand this cell is at a microscopic level and you are trying to deform, and for deformation the force also you can understand, it is only 70 pico Newton, very small force. So, you have to measure also this force. So, you can see when it is healthy it is able to deform. So, it has elasticity, you will be able to deform it. Okay. But if it is infected by this malaria inducing parasite P. falciparum, okay, then you see that it has become hard. Okay. And in the bottom figures, these three figures, if you see, okay, the cell is now hard, again these two tweezers are there, they are trying to stretch it, but they are not able to stretch it. So, this one is infected with a parasite and the top one is not infected with parasite. So, it has elasticity. So, you can understand that just by infection the cell behavior has changed. okay, and it is not a chemical change, it is a mechanical change. I am able to see that I am not able to deform the infected one, but the healthy one is able, you are able to deform. Okay. So, this type of analysis can also be done to know that whether somebody is infected by some disease or not. Okay. So, again another idea for material behavior taking from biotechnology. Now, taking for electronics for example, okay, we have a lot of fancy idea about electronics, okay, you can do this and you can do that, okay, but again the basis is material development, okay, because all the semiconductors which are developed using silicon, of course. So, silicon is an intrinsic semiconductor and you add dopant to make it a extrinsic semiconductor, and this dopant can be pentavalent doping elements or trivalent doping elements, and depending upon which you are adding, you can have either P type semiconductor or N type semiconductor. Okay. So, but to get this semiconductor you do not want any other impurity in silicon, okay, otherwise all the properties will not be there which you want. Okay. So, you want only that type of property, either it has to be a P type, that means lot of holes, or it has to be N type, means lot of electrons. So, silicon has to be very pure for that, okay, and to get this silicon, pure silicon, the only technology is the zone refining, and which is based on only on the metallurgical concepts, okay, of phase diagram and non-equilibrium phase transformation. So, these two ideas actually give you this high purity silicon, and the purity can be 99.999999, I think I have covered all the 9s, and percentage. So, you can understand that the impurity level is at around 0.000000, again if I have missed one 0, you can add 1.00001% is the impurity level in this. So, you can understand the kind of purity you can get or you need in silicon to have a good semiconductor, okay, and when you have a very high purity silicon, only you will get a good semiconductor, extrinsic semiconductor. So, that when you add this dopant, okay, you get either P type semiconductor or N type semiconductor, okay, and one zone refined tantalum single crystal is shown here. Okay. So, you can get single crystal also by this particular technique, which is what is used in all these solar panels and all that. You must have if you have are looking at some technical aspect of solar cell, they want a silicon single crystal, okay, then only they get very good efficiency. If it is not single crystal, it will perform as a solar cell, but the efficiency will go down. Okay. So, one example of tantalum single crystal is shown here. You can see the finish, the shine on this surface compared to the other products which are shown here, and it is around 99.999% purity. Okay. So, again for electronics you need material, you have to depend on the metallurgical concept to get those materials. Again, as I told you, if somebody started using in advertisement, that means that idea is in vogue, okay, or that field is in vogue. For example, all these recently launched cars, they are advertising that they are using now advanced high strength steels, okay, for of course they have very high strength, so you can reduce the weight of the car. At the same time, when you are having any unfortunately any car accident, so under those impact, it is able to withstand the crash, okay. So, it will not crumble, okay, it will be able to withstand the crash, okay. Recently also you must have come across in the newspapers that none of the Indian cars are able to withstand the crash impact, okay. So, now they are going to this for this high advanced high strength steels, which has very high strength, and by that they are able to reduce the weight. So, of course, their fuel economy is going up. At the same time, they are having very high strength, so they are able to withstand the impact during any crash. Okay. So, again if you see the recently launched cars, and if you go to their websites, you will see that for the exterior and the structural component, they are advertising this, that they are using this kind of materials now. So again, earlier nobody was talking about any material, now they are talking about material, and that is a good sign, okay, that the material development is there, new requirements are there. Okay. So in my introductory lecture which I gave, there also I talked about that your government policies keep changing. Okay. So for example, they will say that now the environmental impact of your car should be this much. Okay. So its emission should be this much. So for that you have to reduce the weight. So you have to develop new materials to reduce the weight. So whatever you were doing earlier, you have to change it. Okay. So these are dynamic fields. It will keep changing according to the environmental concerns, government regulations, and so on. Okay. Another example of materials or materials concept is material failure. Okay. And another, again, one of the very popular example is the failure of Titanic. Okay. So it's in maiden voyage itself, it unfortunately it sank. Okay. And the reason for that was that the ship was going through very cold water in Atlantic. Okay. Atlantic is very close to the North Pole, and one iceberg, a big iceberg came and hit the ship. Okay. So normally if you have a good material, that is what you see in the cars also, if you have a small, you have experienced a small accident, your car has experienced a small accident, you will see a dent only. Okay. It will not break into two parts. Okay. So normally if iceberg hits, okay, unfortunately you should have a dent at most. But in this case, actually it fractured, it started cracking. Okay. And under the heavy load, that this was the biggest ship of that time in terms of the weight. Also it was the most powerful ship of that time, so its velocity also must be very high, and they wanted to reach USA in a particular time. So they were also, I think, going at very high speed. Okay. So very big mass, big velocity, and when it hit the iceberg, so the energy of the impact must be very high, the momentum must be very high. So it is a impact kind of loading. Okay. But if you have a good material, there won't be any problem. The problem was that at that time, the whatever steel they were using, it had very high sulfur and phosphorus content. Okay. And when you have this high sulfur phosphor content, what happens is that your low temperature properties are not good for that steel. Okay. So actually steel start behaving like a brittle material at low temperature. So under in that temperature of Atlantic Sea, okay, the temperatures were very low, so it behaved like a brittle material. So when that iceberg hit, the fracture started, and under the weight of the ship, it started growing, and then the whole ship broke into two parts. Okay. So there is a brittle transition. So what otherwise a material should have behaved as a ductile material, now it is behaving like a brittle material, and that was the cause of the this accident. Okay. In fact, the material failure ideas you can also use for some very good purpose. For example, this in Mahabalipuram there is a big pond, or you can say a tub like that in a single rock. Okay. And you can see the finishing and the curvature they have got, very nice circular curvature with a very good finish. And you must be wondering that at that time, it is I think 400-500 years old, how they produce this kind of nice surface finish and nice circular curvature. Okay. And for that they were using the concept of failure of materials also only. Okay. So the rock is again a brittle material, it behaves like a brittle material, so it can be easily, if you hammer it, it will fracture into multiple parts. If you take a good ductile material, let us say aluminum, and if you hit it, it will not fragment into multiple parts, it will just deform. Okay. So what they used to do, they used to have these holes, okay, as you can see here, lot of holes, and then they used to put a wooden bag into that, okay, and after that they used to pour hot water, okay. So, because of this wooden bag and you are pouring hot water, it used to expand, okay, and when it used to expand, it used to apply stresses on this, you can say, ligaments which are left, okay, and because of that stress, this part used to fracture. So, whatever profile you want, for example, here you want a circular profile, you make these holes, okay, and then when you do that, what will happen, that the whole thing will fracture, okay, and you will get a very nice surface finish, okay. So, very interesting technique to get huge shapes like this, okay, in a single rock, okay. Now, according to me, you will be able to appreciate and understand materials much better if you think that they also behave like what we do, okay. So, if you bring a human perspective to the whole understanding of the materials, okay, it will be, you will be able to appreciate that what does it mean, why, or how I can easily understand the material behavior if I compare it with the human behavior, okay. So, for example, if I take simple 4140 steel, okay, if I do an annealing, this is one kind of treatment, okay. So, if I do an annealing, I get a strength of 415 megapascal, okay. If I do a, after heating and then quenching, means I am doing a very fast cooling, okay. In this case, in annealing I am doing it a very slow cooling, okay, then I am getting a lower strength. If I do the same treatment, I take to high temperature, but now I am quenching this material, okay, then I get very high strength, okay. So, the same material, but two different treatments were given to it, okay. So, one turned out to be low strength, another turned out to be high strength, okay, and I usually kind of jokingly compare it with the 70s movies, okay. Usually in 70s lot of movies had these stories that twin brothers are there, one went to the police officer's house after, of course, getting separated from their family in Kumbh Mela, and one went to the maybe dacoit's home, okay. So, one turning out as a good citizen, another is of course doing bad things, okay. So, two different condition, okay, starting from the same family or from the same, you can say, condition, but two different conditions were imposed. So, one turning out to be something else, one turning out something else, okay. So, same material done, if you do annealing, it is a different strength, if you do quenching, it is a different strength, okay. Another example, okay, and this is for fatigue, okay. Fatigue is a kind of a material, kind of a condition imposed on the material where it goes under cyclic loading, okay. So, continuously the loading cycle is changing, as I told you the example of shaft of the automobile where it is rotating. So, it goes from tensile to compressive to tensile to compressive and so on, okay. And when you have this kind of condition, the material fails at much lower load, okay. So, much lower than its yield strength also, which you get from a static condition, okay. So, it will fail at much lower load, okay. So, again I compare it with kind of a, for example, a traffic jam, okay. So, if you are in a traffic jam, you are continuously maybe honking or others are honking their horn, okay. Also you continuously you are changing the gear, you are pressing the clutch, sometimes you are pressing the brake or you are pressing the accelerator and so on. So, it is a continuously changing condition for you, okay. And suppose in that somebody comes in front and blocks your or cuts in front and blocks your way, okay, you will feel very agitated, of course, okay. And suppose normally you are very silent guy and you do not get agitated much easy, in that condition you will get agitated by a small incident like that, which you will not do in a normal circumstance. Okay, so that fatigue on your mind, that you are continuously doing this operation, okay, make you agitated at much lower threshold. Okay, so your threshold has come down. Okay, so this is one of the case condition where again you can very nicely relate it with the material behavior and how the human behave in the similar conditions. Okay, and both have the same type of behavior issues. Okay. Now you must be wondering why I am putting Hrithik Roshan here. Okay, I am taking it as an example of work hardening. Okay, this is one of the way to increase the strength of the material by working on the material. Okay, so if you take a aluminum small sheet and you hammer it. Okay, so earlier you may be able to deform it very easily, but after hammering you will see that it is now very difficult to deform it. Okay, so basically you have done some working on the material. Of course, at a microstructural level there are a lot of understanding you have to gain to understand this kind of behavior, but if you just see at a macro level, you are seeing that after you have hammered the material, now it is very difficult to bend it, for example. And you can again compare it with the people who do bodybuilding. Okay, they have to work on their muscles. Okay, so you keep pumping the iron, okay, and you will see that your muscles are developing, your strength in the muscles are developing with working. Okay, so again in material also you do working and you get hardening, you get very hard material. For humans also, when they work, their muscles strength increase. Okay, so there is a hardening. Okay, you can feel it that the muscles are getting hard. Okay, so again you can see that very nice there is a very nice correlation between how materials behave, how human behave in the similar conditions. Okay. Now to end this lecture, I just want to again bring a new flavor to it, to the idea of the materials. Okay, that suppose you take this very popular example, Nano, which was launched by Tata at one time, and suppose now you can see there are a lot of materials here. For example, bonnet is some steel sheet is there, some glass material is there, some plastics are there on the bumper. Okay, suppose I want to see that what is inside this this material on the bonnet. Okay, what is inside it. Okay, so suppose I am taking magnifying that, going into it. Okay, so what I will see, a microstructure. Okay, so on the surface you do not see anything, but actually inside the material there are a lot of features, there are a lot of things are there. Okay, and you will see some dark areas, some bright areas. Of course, we will see what do we mean by that. So there are a lot of features are there inside the material which you do not see from the outside. Okay, and this is called microstructure. Suppose I am interested to go more into detail of this, that what is at the next level of this. Okay, then I will go at the atomic scale and I see that there are nice atomic arrangement in the material. Okay, so atoms are arranged in a very nice fashion. Okay, suppose I want to say that okay, how these arrangements are there, then I can say that these are arranged in this fashion. Okay, which we call as crystal structure. Okay, so in the subsequent slides or presentations you will see that what do we mean by this. So you can see that as you are going to a smaller scale length, okay, there are more details in the material. So what you see from the outside, actually there is a microstructure. If you go into more details, you see that there are atoms arranged in a specific fashion, and those atoms, how they are arranged, can be classified into these 14 ways, okay, which are called crystal structures. Okay. So with that, I am hope that you will be able to appreciate that the study of materials is a very interesting subject. Okay, and it covers a very wide areas. Okay, and it is very important that the development of materials is very important for a lot of technological developments which are going on right now and which will come later on. Okay. So, the understanding of this material behavior or materials will be very helpful for a mechanical engineer. Okay. So, when he designs or he uses some material, he will be also will be able to appreciate that when he is taking this material, what is happening inside, okay, or why your supplier is giving this material to you, okay, for whatever mechanical properties you want. Okay. So, with that, thank you, and we will see you in the remaining course.